So today we have kind of a lot of topics to cover. So physics honestly has you kind of need to know it on a less deep level. So I didn't include a lot of detail in it so it's not overwhelming. But the topics to cover today are DC circuits, oscillators and waves, and sound. And then these are the topics that we'll be covering. You guys can just use this as a reference to the list, and then the PowerPoint will follow this order. So the first thing that we have is Kirchhoff's laws. So this is something that applies to circuits. Um, so the first law has to do with voltages, and it says voltages around a closed path in a circuit must equal zero. Um, And then the second one says the sum of the circuits entering a node must equal the sum of the currents exiting a node. So that must be a little bit hard to visualize just by reading those sentences. So the next slide, I have a picture. So when you're talking about a node for current entering and exiting a node, so for example, the center point is a node. So A plus C, D and B, because you see the arrows that are feeding into the node. So this is current entering the node, and then E and F, those are currents exiting the node. So all of these four entering the node will equal the two exiting the node. And then the voltage law is a bit less intuitive, I feel like, but it says voltage drops throughout a circuit. So between this point and this point is one voltage drop B, between this point and this point is another voltage drop C. It says all of these five separate voltage drops must equal zero. And this one with the source as well. So an example of that is this diagram saying you have number 5 feeding into this node, exiting this node, and then 1 entering into this path. So what is current I flowing out of this path? So if you guys could try that and put the answer in the chat. And sorry, these numbers are the amount of the measurement of the circuit flowing in. So this is 5 milliamps, 2 milliamps, and 1 milliamp. Yeah, so that's correct. So we see 6 milliamps flowing into the node, 5 from the left, 1 from the right. But there's also that 2 flowing out of this node. So by the time you get to this node, you're only left with 3 from this side and then 1 from this side. So that's correct. Good job. And then I actually don't have any more practice questions for the rest of the content slides. So if at any point you don't understand something, I'm gonna be reliant on you guys to stop me and ask a little bit more in depth. Okay, so this next slide is pretty like surface level. It's just talking about the two different measurement devices you need for a current, or that might come up when discussing current. An ammeter is used to measure current. It requires the circuit to be on, which means your current has to be present, otherwise your current is just going to read 0. And you just plug the ammeter in at the exact point you want to measure current for. And you want to have ideal ammeters that have 0 resistance and no voltage drop across them so that they don't change the property of the circuit itself. Next, we have voltmeters, which measure voltage. Again, the circuit must be on, otherwise voltage would read 0. And voltmeter is a little bit more complicated about where they're inserted. Not that you don't actually need to know this in too much detail, but just know that voltage you have to measure parallel to the 2 points you're actually measuring the voltage drop between. So, um, yeah, the only real takeaway from that is that you insert the voltmeter parallel to the actual place that you're measuring the voltage at. And then ideal voltmeters, on the other hand, have infinite resistance. And like knowing ideal ammeter and voltmeter properties is, I feel like, something that's pretty non-intuitive, and I've actually never seen it come up on like any practice test. So I wouldn't like worry too much about it. Just know these basic facts. Last, we have ohm meters, which measures resistance. For this, the circuit should actually be off. Or, like, more accurately, it doesn't need to be on. If it is on, you run the risk of inaccurately measuring resistance, so ideally, the circuit should be off. So what you do is that the ohm meter has its own voltage and current created at another point in the circuit. So knowing those two facts, you calculate the resistance at the point where you do want to measure resistance. Any questions on that? Again, I feel like this is a very low yield topic. You just need to know this bare bones information. Next, we have magnetic fields and forces. So talking about like what creates a magnetic field, it's any moving charge. So this could be a wire with current or a charge that has velocity. And then there's different types of magnetic properties, or sorry, magnetic material. There's diamagnetic, which um, there's diamagnetic, paramagnetic, and ferromagnetic. Um, this is like more in the chemistry section, so I didn't put this on the slide, but I would just know the definitions of these and know um, the differences between them. Beyond that, you don't have to memorize like which materials are which. Maybe be able to look at a periodic table and see like electron configurations. Um, so the things relevant about magnetism to these different types of magnetic materials is that diamagnetic materials are repelled by a magnetic field. Um, Paramagnetic materials are weakly attracted by an external magnetic field, and ferromagnetism are strongly attracted to a magnetic field. Um, Again, this is not something that I saw come up like too much at all. So again, just know the definitions and be able to apply it to like an electron configuration. From the chemistry sense, I did not prepare that material today, but it's something like half-filled d orbitals or like completely filled d orbitals, something like that. And then the actual part of this that is relevant to the physics is that you need to know the right-hand rules, and there's two of them. The first one is on this slide. So when you have a current in a wire, you can use a right-hand rule to determine the direction of the magnetic field when you know the direction of the current. So let me see your question, even though it's a yeah, so we're not told. So this is not a negative charge because when you have a negative charge, remember that conventionally the direction of current is opposite of the direction of electron flow. Is that familiar to you? Okay. So then it would mean that if we have electrons flowing in this, so if we had a negative charge, it would be flowing downwards. So they've accounted for that by saying it's the direction of the current. That's actually a really good question because if it says for the next right hand rule, if you have a positive charge, your direction would be the same as the velocity of the positive charge. But then if you have a negative charge, your direction of your thumb would be opposite of the direction of the negative charge. So just remember your thumb should be pointing in the direction of current or flow of positive charge. So you point your thumb in the direction of the current and then wrap your forefingers around the current. So, and then from there, it depends on which side of the wire you are on to determine the direction of the magnetic field. So, say I'm on the right side of the wire on this field on my screen. So, at this point, is my magnetic force pointing in or out of the screen? So, I'm on this side of the wire. Your hands are wrapped around it. So, at that point, your fingers are curving into the screen. Does that make sense? Oh, oh, sorry. Yeah, I'm on the Google Meet rather than the. Okay. I was sorry. I was pointing on the right side of the screen. Can you see the cursor now? Okay. So say we're on the right side of the wire. My question was, is your magnetic force on this side of the wire pointing in or out of the screen? Okay, perfect. And then what about on the left side of the screen? Okay, perfect. Yep. All right. That was it for that slide. And then this is the second right-hand rule. Ignore the third. I don't think that matters. Um, Magnetic forces are exerted by magnetic fields on moving charges as well, not just current in a wire. So when you have magnetic field direction, and then you have the direction of a moving charge, which is your velocity. So B is your magnetic field, V is your velocity of moving charge, and then this F is what you're trying to figure out. So your fingers point in the direction of the magnetic field, and then your velocity of the positive charge or current is what your thumb points in, and then your palm shows you the direction of the magnetic force. Okay. Any question on magnetic fields and forces? Great. Next, we have wave properties and speed. So we have the basic definitions of transverse versus longitudinal waves and some examples. So transverse waves are light and electromagnetic radiation. Longitudinal waves are sound, pressure waves. Apparently, also earthquakes are longitudinal waves because I guess they're a type of pressure waves. So transverse means that the wave displacement is perpendicular to the direction of motion. Um, what this would mean is that think about like a normal light wave, it goes up and down. Sorry, let me try inserting that picture real quick. Sorry about that. Okay, so that's our light wave, or any transverse wave. Um, and then for our longitudinal wave, we have something like this. So for our transverse wave, what we mean by wave displacement is that the waves are going up and down while, or sorry, the wave is gonna move from left and right, whereas the particles are moving up and down. So that's what we mean by saying wave displacement is perpendicular to direction of motion. So direction of motion is particle motion, and then wave displacement is wave motion. On the other hand, for longitudinal waves, we have wave movement. Wave motion is also from left and right, but particle motion is also left and right. That's where you get the compressions and the rarefactions. So rather than things moving up and down to create the wave, things are moving side to side. And then in both of them, the wave is moving from left to right. And then we have probably the most important formula for waves, which is velocity equals frequency times wavelength. And then another property of waves is amplitude, which is basically like how high these waves displace from the original point at the x-axis. So the higher the amplitude, the higher the energy of the wave. And then intensity is energy over time squared, which is the same thing as power over area. So amplitude talks about energy itself, and then intensity talks about energy as a distance relative to the source of the sound. Okay. And now we talked about waves, and then interference talks about how waves interact when you have more than one. So constructive interference is when you have two waves that have their points of maximum displacement at the exact same place, like this, and then points of minimum displacement at the same points as well. So they just add up to create a higher amplitude. Oh, sorry, this should say partial constructive. Um, so partial constructive is where it builds up in some points because it kind of matches up, but then it is destructive in some points. So that's why you see it's increasing, say, at this point, and then it kind of decreases at other points. So partial constructive is kind of out of phase. It's not 180 like in destructive, but it is not completely lined up like in constructive. So lastly, we have destructive, which means the two waves cancel themselves out because they are lined up 180 in terms of each other, like relative to each other. But I guess they don't necessarily need to cancel out exactly. Like if one had different amplitude, like say the pink one was higher, then what you would end up with is just a smaller amplitude of just the pink one. So it's still destructive because it's completely going to eliminate the bluer one. So the best way to think about it is that they're 180 degrees relative to each other. Oh, sorry. And then beats are things that occur when two waves exist at different frequencies. So beat frequency is the difference between frequencies of two waves. Again, this is also something that doesn't show up a ton. So I would just know that equation like F prime equals F1 minus F2, where F prime is talking about beat frequency, and then F1 is one frequency, and then F2 is the other frequency. Next, we have standing waves, which are strings or pipes. So we have this pipe with only one end open, or then pipe with two ends open. So this is called an open pipe, and then this is also called a closed pipe. Strings behave the same way as tubes with both ends open. So a node is this point, this point, this point, this point, this point, this point. So point of no oscillation, which basically means like this is your x-axis and there's no displacement at the, or sorry, it means there's no motion. So when you have a standing wave, it's that string is like moving constantly, but at these points of nodes, there is no movement. Whereas antinodes, that's where you're going to get maximum oscillation. So this point would go like up and down, up and down. So that's the maximum oscillation. Another thing to know about these waves, these standing waves in strings or pipes, is just the equations. So let me take a pause right here and pull up this equation sheet, which I can share with you guys in the chat. Sorry, just give me 1 second. Okay. I think you guys should be able to see this. All right, so the two equations that are relevant to us right now is we're talking about pipes and open pipes and closed pipes. We need to be able to find the wavelength at a certain frequency, or at a certain harmonic, sorry, and then frequency at a certain harmonic. And by harmonic, what I mean is the number that we're looking at. So the first one is called the fundamental harmonic, and the frequency of that is called the fundamental frequency, and then everything on is called 1 and 2, and so on. So you can see the difference between open and closed pipes. For open pipes, it's 2L over N. For closed pipes, it's 4L over N. You do have to have these equations memorized and be able to recognize what open pipes and closed pipes are in order to be able to say, a lot of times what they'll do is they'll give you fundamental frequency of an open pipe, right? So then you should know to use this equation to find the wavelength of the fundamental frequency. And then you can use that to find L. And then what they'll ask you is find the wavelength or frequency of the second harmonic. And so you would plug back in that length here and then just do divided by 2 rather than divided by 1. Does that make sense? And then let me drop in this equation sheet. Thought I could send it here. Okay, I'm not able to drop this in the chat, so I'll put this in the YouTube description. But I found this equation sheet like super helpful just to have everything in one place. So I would recommend using it. Let me go back to sharing the PowerPoint. Okay, I believe this is the last slide. The last concept that we have is the Doppler shift. So this phenomenon describes how your observed frequency is different than actual frequency when either the source of the sound or the observer are in motion. So the most common example is like an ambulance. So say you're standing somewhere and you have an ambulance coming towards you. The pitch seems higher than the actual pitch of the siren because it's coming towards you. And then once you're lined up with the ambulance and then it's going away, the pitch seems to get lower than its actual pitch. And that's all having to do with the relative motion of the ambulance. So when it's coming towards you, that's going to be a positive BS. And then in this case, you're the observer, so VO would be 0 because you're stationary. So you can see here when you have the positive VS, so your ambulance is coming towards you, you would subtract that. So then when you have V over V minus VS, your denominator is getting smaller, which means overall this term is getting bigger. So your observed frequency is going to be higher than your actual frequency. And that explains why when the ambulance is coming towards you, the pitch seems higher than what it really is. And now when it's going away from you, that's going to have a negative velocity. So that at that point, you are adding to the denominator. So it's negative. Yeah, so it's negative. Use negative when it's coming towards you, and then positive when it's going away from you, the observer. So then your denominator would be getting bigger when it's going away from you. So this overall term is getting smaller, which means your f prime, your observed frequency, is less than your actual frequency. Yeah, so I think this honestly just takes some practice. You guys have any questions on this? Yeah, sorry. So when you are stationary, you just make sure that your V0, oh, sorry, I keep pointing on the Google Meet. Okay, sorry. So VO would just be 0 because you're not moving. So then the numerator would just be V, and then the change would just be happening in the denominator. So this V is the velocity of the actual sound. So this would always be the speed of sound in air. So these are constant, they don't change. This VO is V of observer, and then this velocity of observer, and then VS is velocity of the source. So like I was saying, for the source, you subtract it when it's coming closer to the observer, and you add it when it's going away from the observer. And then for the VO, you add it when it's coming closer to the source and subtract it when it's getting away from the source. So that's why you see it's plus minus minus plus because they're opposite. So VO you add when they're getting closer, and then VS you subtract when they're getting closer. And that just has to do with the equation. One is in the denominator, one's in the numerator. So you should always just know that if the observer and source are getting closer together, your observed frequency will be higher than your actual frequency. If they're getting farther apart, your observed frequency should be lower than your actual frequency. Okay, so now we have a passage. Um, I'm going to give you guys some time to read through this. And then I'll also, yes, sorry. Where did you see overtone? Why can I see this? Chemistry, where do you see that? Oh, okay, yeah. Do you want to describe the problem, or I think you should be able to screen share if you want to. That would be great if you could.
I had this question like a long time ago, so I'm not sure where the question went,
Okay.
but I'm just wondering if you could explain like what an overtone is. They were basically saying like um, I just remember the question being like, oh, you just have to add +1 to whichever harmonic you're in to get the overtone, but I didn't really understand what an overtone meant.
Okay, let me. So not this one, right? It would be the one for harmonics. This one?
Yeah, yeah, this one.
Oh, okay, okay. Yeah, I'm not too familiar with that sound, so let me just make sure. So overtone is a term generally applied to any higher frequency standing wave, whereas the harmonic is reserved for those cases in which the frequencies of the overtone are integral multiples. Oh, so it's saying something like, hmm, this is a good question. Where do you remember like what source that was from? Was it an AMC question? Okay. I'm trying to get that. Let me share this picture. So was it something like this where the fundamental mode is the first harmonic, the first overtone is the second harmonic? I guess that goes with like adding the one to the overtone to get the harmonic. Are you there?
Oh, sorry, I was muted. Yeah, this is what I was talking about. But I
Oh,
just didn't understand what was going on. Like, what does an overtone mean?
I think it's just a definitional thing. So like see how the second harmonic is the first overtone.
Mhm.
I honestly don't remember anything ever being called an overtone in the practice questions with AMC or U World. So I'm hoping it's like you took like a third party question somewhere and
Yeah,
it's
it was
like
from Princeton Review.
okay.
So I'm just guessing I should just remember that that's what an overtone is.
Yeah, honestly, like I've never seen it anywhere, but I guess like because you've come across it, you might as well know it. There's nothing more to know about that other than you just subtract one from the number of harmonic to get the overtone. It's just terminology basically.
Okay.
Okay, thank you for asking. And then if you have any other questions, if not, I'll give you guys time to read through this passage and then feel free to look through the questions if you want. And then I put the link in the chat, or you can also just read on the screen. And then once you guys are done reading, if you could just put a message in the chat, and then we'll come back and read through it together. Do you guys need more time? Okay, perfect. All right, so I'm gonna quickly go through the passage, and then if anyone has any questions about like a certain thing, stop me. So it says, using the Doppler effect, it is possible to measure motions within the body. The ultrasonic flow meter is a medical device that can approximate the velocity of blood flow in a particular vessel. The transducer of ultrasonic flow meter is composed of both a transmitter and a receiver component. Ultrasonic waves of a set frequency are emitted by the transmitter and which are then scattered by the moving red blood cells that they come in contact with. These scattered waves return to the receiver with the frequency altered by the Doppler effect. Figure 1 just depicts how an ultrasonic flow meter functions. So we have the set frequency going out, being scattered by the red blood cell movement. So this indicates velocity of the red blood cells, and then being sent back with the altered frequency. The Doppler frequency F Doppler, the difference between the received frequency F prime and transmitted frequency FO can be estimated from the following equation, where V RBC is the velocity of red blood cells, theta is the angle between the transmitted ultrasonic wave and the motion of RBC, shown here, and C is the speed of sound moving through soft tissues, which is approximately 1.5 times 10 to the negative 10 to the 5 centimeters per second. Blood flow can be characterized as either laminal, plugged, disturbed, or turbulent. Laminar blood flow follows a parabolic pattern with the greatest flow velocities being greatest at the center of the vessel. Plug flow is seen in vessels with large diameters, such as aorta, where the velocity of the flow is relatively uniform throughout the vessel. In a disturbed flow, RBCs no longer travel in straight lines. However, in general, they continue to move in forward direction. Turbulent flow is chaotic and random, with RBCs flowing in all directions at varying velocities. Ultrasonic flow meter are useful for measuring blood flow velocity, but not blood flow volume. Which following state? Oh, sorry, that's the first question, isn't it? Yeah. So ultrasonic flow meters are useful for measuring blood flow velocity, but not blood flow volume. Which following statement best explains why this is so? Do you guys have an answer for this one? Okay, perfect. Yeah. I honestly thought this was a really hard question, so I didn't have a lot of things to work off of. So basically, I looked at, okay, there's blood velocity and blood flow. I was just thinking about like what connects those, and that would be cross-sectional area. Whereas, okay, yeah, let me explain that first. So ultrasonic flow measures blood flow. The continuity equation links Q, which is blood flow volume, to area of the blood vessel, to V, which is blood flow velocity. So we need cross-sectional area to determine blood flow volume, but if the A isn't constant, then it makes it harder to calculate Q from the continuity equation. So we found a link using an equation that we should know, and then the rest of the options, B, C, and D, have nothing to do with linking blood flow velocity to blood flow volume. So B is not indicated. Even so, spectral broadening does not link velocity to volume. And then cell-to-cell interactions, viscosity does not link velocity to volume either. Viscosity actually directly impacts velocity itself because it's talking about resistant to flow of fluid. And then speed of sound being greater than speed of moving RBCs is not relevant to velocity or blood volume. So well done with that. Next question is also a bit challenging, and it's entirely based on the passage. It has nothing to do with background knowledge. So spectral broadening occurs when Doppler shifted frequencies exist over a wide range of frequencies rather than at a single frequency. Which of the following types of flow is most likely to exhibit the greatest amount of spectral broadening? Did you guys get anything for this one? All right, perfect. Did you want to explain that at all, Tanushree?
I just took it right out of the passage where I believe it says turbulent flow is chaotic and random with RBC flowing in all directions at varying velocities. So I just used that piece to answer the question.
Yes. So what is the link of RBCs and all velocities to frequencies of Doppler shifted frequencies? So we just have to go back to the picture and see if you have velocity of RBCs pointing in all directions, you're going to get a bunch of free F primes. So instead of just having one velocity, direction, and speed, getting one line back, if you have a bunch going this way, then you're going to have a bunch of F primes going back. That has to do with a wide range of frequencies, a wide range of Doppler shifted frequencies, and that's correct. You were looking in the right place, just one more piece to link it all together cleanly. And this was the explanation straight from Khan Academy. So when flow produces a wide range of values for V of RBC and theta, so theta is talking about the direction. Turbulent RBCs has, yeah, basically what he said. So thank you for sharing your thoughts. And the next one, if a 1 microhertz ultrasonic flow meter is used to measure the blood velocity in the aorta, what will be the received frequency if the transducer is oriented perpendicular to the aorta?
I didn't really understand this question. I'm wondering if you'd go over it.
Yes. All right. So ultrasonic flow meter, receiver, transducer, and aorta. Okay. So here is the blood vessel. So this can be your aorta. And then, what was it? Sorry for going back and forth. Transducer. Okay. So transducer. Okay. See, it has to do with this theta. So rather than the transducer being at this angle, if it was perpendicular to the blood vessel, it would be right here. So the angle,
0, right? The cos would be 90, so then it would be 0.
Yes, perfect. Yeah. So it's noticing this picture and then plugging it back into this equation.
Like that part I got right, but then I just didn't understand why the answer was 1. Like they said it was.
Oh, okay. Yeah. So that has to do with it's 1 microhertz ultrasonic flow meter. So remember that this is F Doppler is what you got to be 0. And then F Doppler is a difference between the received frequency and the transmitted frequency. So what you're given is a transmitted frequency, 1 megahertz, and then the question is asking you for received frequency.
Oh, okay.
Yep. So I guess there was one more step. Yeah, so F Doppler from cosine 90 gets you 0, and then F Doppler is the difference. So if the difference equals 0, the transmitted frequency will be the same as your Doppler induced frequency. Oops, sorry. So question 4, what additional information is needed to determine the time it takes for an emitted ultrasound to return back to the ultrasonic flow meter? So I have up here time equals distance divided by velocity. Velocity of the ultrasonic wave is provided. Is it provided? Is that the 1.5 is what's provided? How did you guys do this one? Did you get this one? I'm pretty sure it's that 1.5 times 10 to the fifth centimeters per second that they're talking about. Does that make do you guys agree with that? So then if we have the velocity, which is 1.5 times 10 to the fifth centimeters per second, and we want to calculate time, we're missing the distance between the transducer and the blood vessel. Correct answer is B. Frequency, it's kind of similar to that first question we were talking about, what links blood velocity to blood flow, blood volume flow. So angle doesn't link time to velocity. Frequency doesn't link time to velocity. And then distance. Wait, sorry, I did the wrong thing. Yeah, this should be D, right? Let me check. Yeah, this is not, sorry, this was, yeah, this should be D. Because velocity of the blood flow, you don't need. You're trying to find you have velocity of the ultrasonic wave, and you're trying to find the distance for the ultrasonic wave. So the velocity of the blood flow wouldn't help you. Okay. All right, last question. Sorry for running over time. According to figure 1, which is a true statement if the angle is between 0 and 90 degrees? So again, we're using the equation. Oops. Okay, here. If this angle is 0 and 90 degrees, what is that going to make your F Doppler? And then how is that going to determine your relationship between F prime and FO? So cosine 0 is 1, cosine 90 is 0. So your cosine theta is going to be positive. So your overall F Doppler is going to be positive. So F Doppler equals F prime minus FO. So for their difference to be positive, F prime has to be greater than FO. Any questions on any of these questions? Or any of the content in general? I'm going to stop recording.